All right, today we're going to take a look at three examples actually of integration by parts. So here's our formula for integration by parts, and I'm not going to go through it now because we talked about it in class the other day, but this formula comes from the product rule. So what we learned real early on in AB calculus, if we start with that product rule and we integrate with a little bit of algebraic manipulation, we end up with this, which is the formula for integration by parts. So the integral that we're trying to evaluate is here, and the resulting solution is here. So the part of the integral that we see here is our given integral. Okay? So what we need to do with that given integral is identify some expression to represent u, and we're going to write that in here. And then we need the other part of that expression to represent dv, and we're going to write that here. And notice what we need to do with u and dv. From u, we need to identify what du is, the derivative of u, because that's used in our solution. And we also need to identify what dv is, because notice if we integrate that, we have v, and that's used in our final solution as well. So with u, we have to differentiate, and with dv, we need to integrate. And we have to kind of pick and choose in here. And so just to make a long story short, whatever we choose for u, we don't want it to get messier if we differentiate it. It can stay similar or get easier, but if it gets messier, we're probably not doing the right thing. And then with dv, we want to integrate it. So if it gets messier upon integration, probably not the right choice. We want to either keep it similar upon integration or more simple. Okay? So in this case, think about it. Secant squared x, if we differentiate it, we can do that, but it actually gets messier. Okay? And if we plug an x in for dv, we know the integral of x is 1/2 x squared, and you're like, it's not a big deal, but which one's messier, x or 1/2 x squared? 1/2 x squared. But notice the alternative, the opposite of that. What if we chose u to be x? What's the derivative of x? 1 dx. That got more simple. And what happens if we choose dv to be secant squared x dx? What happens if we integrate secant squared x dx? We have the tangent of x. That got simple, more simple. Okay, so this is the right choice for this integration by parts because differentiation got more simple, integration got more simple. So now we're going to use our formula. The result of this initial integral is u times v, here's u times v, minus the integral v du. v du. So here that is. Okay, so final answer here. So this tangent integral, some of you might have memorized it last year. I'll mention it is a u substitution type question, since the tangent is sine of x over cosine of x. This is a du over u question type integration. So that result is going to be the negative natural log of the absolute value of the cosine of x. Again, this is an integration by parts lesson, so if you have questions on this part, we'll talk about it in class, or you can come outside of class and we'll talk through this just to remind you. Okay, so the result of this is minus the opposite of natural log. So that double negative, we have a positive natural log of the absolute value of the cosine of x, and then we follow up with that plus c. You might have forgotten about that too. But we have an indefinite integral, so there's that unknown constant that's added to the end there. So we are done. You might be asking, well, why weren't we done right here? We used the formula. Well, we're trying to solve an integral, so our answer, our end result, should not have an integral in it. So if once we use integration by parts one time, if we have an integral, we need to finish that off, and we did. All right, let's look at the next one. It looks kind of simple, the integral of the natural log of x dx, and you might be thinking, well, didn't we learn that in AB calculus? No, we worked with the natural log a lot, and it looks very simple, but one method to get through this integral is to use integration by parts. So we're going to identify what u is, and we're going to identify what dv is. So we have, actually there's two expressions here. There's a natural log of x expression, and there's a dx expression. So think about this. What if we make u equal to the natural log of x? Do we know what the derivative of the natural log of x is? Yeah, it's 1 over x. What if we made dv the natural log of x? Do we know what the integral of the natural log of x is? Well, look, that's what we're actually trying to figure out there. Okay, so the logical choice in this case is to choose u to be the natural log of x, because we know the derivative is 1 over x dx, and what's left to integrate? Dx is left to integrate. So what's v equal to? X. So now we're going to use our formula for integration by parts. What is it? It's u times v, so equals u times v minus the integral of v du. So v du. Let's simplify that a little bit. So we have x times the natural log of x minus the integral. Simplify, that's 1. Final answer, plus c. All right, we're going to finish off. I'm going to pause this right here, and I'm going to continue. I have one more example for you. It takes a little bit longer, so I'm just going to make another video for that one.